In this second video on Lewis electron dot diagrams, we're going to start by practicing, looking at a few examples, and then we're going to extend our understanding by looking at two special topics related to this called resonance and formal charge. So let's just start with a few examples just to quickly practice Lewis electron dot diagrams. You can pause the video after seeing the example and try drawing the diagrams yourself if you feel you understand what you're doing. Start with HCN. Okay, remember that Lewis diagrams are intended to show how molecules, so covalent compounds, are connected, the atoms in them are connected or bonded to each other, and to account for the electrons, the valence electrons that are involved in the bonding. In HCN, we'll assume that the carbon is the central atom there. Hydrogens can never be central, they have to be terminal, they have to be bonded to the central atom. So this is going to be a hydrogen bonded to carbon, bonded to nitrogen, like that. In most examples that we will see, the first atom is usually the central atom, but in this case it's the carbon that is central. So we count our valence electrons, do an accounting of them. These are the electrons involved in bonding. So the hydrogen atom is one of them. On the periodic table, there's one valence electron for hydrogen, so we have one electron from hydrogen. We have one carbon atom in this molecule, so there's 4 valence electrons per carbon atom. Their electron configurations end in S2P2, so there's 4 valence electrons. So 4 electrons total from carbon. And then we have one nitrogen atom, which brings 5 valence electrons. I'm looking at the periodic table when I'm determining how many valence electrons there are per atom. Nitrogen's configuration would end in S2P3, so it's got to have 5 valence electrons. So we have a total of 10 electrons to play with in this molecule. In bonding hydrogen and nitrogen to the carbon, we've already used up 2 and 2. We've used up 4 electrons. Each bond represents 2 electrons. So we have 6 electrons remaining. Recall that hydrogen obeys what's called the duet rule. It's satisfied with just 2 electrons, and it has 2 electrons right there in that bond. Carbon and nitrogen are in period 2 on the periodic table, so they follow the octet rule and they never break that rule. You never get more than 8 electrons for elements in period 2. So carbon, carbon needs, it has currently 4 electrons, it needs 4 more. Nitrogen currently has 2 electrons, it needs 6 more. So we need more electrons than we have. Therefore, we're going to resort to putting in higher order bonds. Let's try a double bond. Now the carbon has 2, 4, 6. It needs 2 more electrons. Nitrogen has 2, 4. It needs 4 more electrons. But by putting in that another bond, we're reduced to having 4 electrons left. So we still don't have enough electrons to satisfy the octet rule for both carbon and nitrogen. Let's try a triple bond. With a triple bond, carbon is now satisfied. It has 8 electrons, 2 here and then 2, 4, 6, 8 electrons total. Nitrogen currently has just these 6, so nitrogen needs 2 more electrons. When we put on that second bond, that left us with 2 electrons, and we can give those 2 electrons to the nitrogen atom. These 2 here by themselves are referred to as a lone pair of electrons. And here we have 3 bonding pairs in that one triple bond. And here's another bonding pair here between the carbon and hydrogen. So we realize in the localized electron model of bonding, we talk about pairs of electrons in bonding and by themselves as lone pairs. Another example, before we look at the 2 new topics, how about Te tellurium F5. Te F5, and it has a charge of -1. So pause the video and try drawing its Lewis diagram. tellurium would be the central atom here, and we have 5 fluorines bonded to it. And now let's do some electron counting. Tellurium is in the same family as oxygen, so it's going to have 6 valence electrons like oxygen does. So we have 6 electrons from tellurium. We have 5 fluorine atoms. They're halogens, part of the halogen family, and all of the halogen family bring 7 valence electrons each. Their electron configurations end in s2p5. So we have 35 electrons from the fluorines. If we add that up, that gives us 41 electrons, which is a little different because it's an odd number. But then we noticed the whole thing had a charge of -1. This was TeF5 minus. That minus sign means we get to add 1 more electron. The reason it's -1 is because there's an extra electron. If that were 2 minus, we could add 2 more electrons. If it were 1 positive, we would subtract 1 electron here. So we have 42 electrons to play with this molecule. Now we've already used 2, 4, 6, 8, 10 in those bonds. So if I take away 10, we're left with 32 electrons. Now the fluorine atoms want an octet. Clearly the tellurium in the middle has more than an octet. It's got already 10 electrons around it, and that might be bothersome, but we notice on the periodic table that tellurium is in the 5th period, and we recall that for any element in period 3 or lower, they have not only the s and the p orbitals for bonding, but they also have d orbitals for bonding. If you are in period 2, you've only got s and p orbitals, 2s and 2p, so period 2 will never have more than 8 electrons. Any element in period 2 will never have more than 8 electrons. But tellurium is in period 5, so it can actually have d electrons in the bonding as well, so the fact that we currently have 10 electrons is not a problem for tellurium. We call that an expanded octet. If we give each of the fluorines their octets with 6 electrons, 3 lone pairs each, 5 times 6 is 30, so we're using up 30 of our 32 electrons. That gives us 2 electrons left. Currently, the fluorines have all got their octets, so they're satisfied, but I have these extra 2 electrons, 1 extra pair. The rule we learned in our previous lesson was if you have extra electrons, put those pairs of electrons on the central atom, in this case the tellurium. So the tellurium has a total of 6 electron groups around it, 5 bonding pairs, and then this 1 lone pair. Because the whole thing is an ion, we put its Lewis diagram in brackets like that, square brackets, and we indicate the charge outside. So there's the Lewis diagram for TeF5 minus. Alright, so let's take a look at a couple of new topics. The first one is called resonance. And let's introduce the idea of resonance with an example. Okay? We'll take a look at the diagram, the Lewis dot diagram for nitrite, NO2 minus. If you try drawing this diagram, what will we come up with? Well, we have a nitrogen with 2 oxygens bonded to it. And if we count our electrons, our valence electrons, we have 1 nitrogen, which is 1 times 5 electrons, so we have 5 valence electrons for nitrogen. We have 2 oxygens, 2 times 6 is 12 valence electrons there. So those 2 elements are bringing in 17 electrons total. But this ion had a negative charge. So because it's negative, -1, we're going to add 1 more electron because of that negative charge. So we have 18 electrons total to play with. We've already used up 2 and 2, so we've already used up 4 electrons, leaving us with 14 electrons remaining. If we look at the 2 oxygen atoms right now, they each have just 2 electrons, so to get their octets, they would each need 6 more electrons. That's going to use up 12, But the nitrogen needs 4 more electrons itself, so we don't really have enough electrons to do that. To solve the problem, we go to a multiple bond, we try a double bond, and we realize that's going to work. With this double bond, I could now give oxygen its octet with 2 lone pairs. I can give this oxygen its octet with 3 lone pairs, and the nitrogen in the middle, I can give its octet with 1 lone pair. If I count up those electrons now, we've got 2, 4, 6, with the oxygen, 8, 10, 12, 14, 16, 18. Those were the 18 electrons we had to play with. Because it's an ion, we put it in brackets and put its charge outside. Now, where does resonance come in? The problem is that we've suggested in this diagram that there's, in the nitrite ion, 1 single bond, NO, and 1 double bond. That would suggest that there's 1 bond which is longer, the single bond, and 1 bond which is shorter, the double bond. When you actually measure the bond lengths of nitrogen and oxygen in this ion, measurements suggest that these 2 bonds are actually the same lengths. They're not longer and shorter. And to just complicate things further, the bond length is actually longer than the length of an NO double bond, but shorter than the length of an NO single bond. It's as though it's some kind of average in between those 2 lengths. So the 2 bond lengths by experiment are shown to be equal, by measurement rather, and not only equal but intermediate in length between a single and double bond. How can we explain that? The answer is this concept of resonance. Basically, what we're going to suggest, and I'm going to draw some curly arrows to show what I'm doing, we're going to suggest that over here on this oxygen atom, 2 of the electrons, 1 of the lone pairs, basically comes down like this to form a double bond here. But this double bond causes a problem for nitrogen. It would mean that the nitrogen atom now has 10 electrons instead of 8, and we know that nitrogen in period 2 can only ever have a maximum of 8 electrons. So if this pair of electrons moves down here, nitrogen needs to lose a pair of electrons. So what happens is over here in this double bond, a pair of electrons move over here to the oxygen. So basically what you end up with is a diagram that suggests that the double bond is actually not the bond on the right, but the bond on the left. And there's another diagram, another Lewis diagram for this molecule. Notice that these are two Lewis diagrams where the position of the single and double bonds are different. It's the only real difference between them. Otherwise, they're equivalent. They're equivalent in that they have the same number of single and double bonds in total, and that one can be changed into the other simply by this movement of electrons, these delocalized electrons that are able to move within the molecule. We say that the actual NO2 molecule is a resonance hybrid of these 2 resonance structures. Each of these 2 diagrams is referred to as a resonance structure, and the actual NO2 ion, NO2 minus ion, is a hybrid of them. That would explain why we don't in fact see single and double bonds, but in fact we see a hybrid, we see an average of the 2. And the actual bond is, the actual molecule is something with bonds that are not single or double, but sort of a 1.5, if you want to think of it like that, bond strength. Anything else I need to say about that? So resonance basically is a way to explain when you can have more than one Lewis diagram showing equivalent structures. So basically equivalent again because the number of bonds, single and double, is the same, and the only difference between these is the positioning of those bonds, the movement of electrons as I've shown. Another related topic is called formal charge. Formal charge. And it's basically a way to distinguish between competing Lewis diagrams. Its usefulness comes in when you've got to choose between two diagrams that are not equivalent. Okay? There are two different Lewis diagrams that appear to be possible for the same molecule. For example, let's consider NO2 positive instead of NO2 negative. We have nitrogen again with two oxygens bonded. We had before, we'll just quickly recount. One nitrogen is 5 electrons, two oxygens is 12 electrons, and that gave us 17. Before we had a -1 charge, so we added an electron. Now we have a +1 charge, so we're going to take away an electron. We have 16 electrons to play with. If we try drawing the NO2 molecule with 16 total electrons, we have 2, 4 already, so we've got 12 electrons remaining. If we try to distribute them symmetrically around the molecule, what do we come up with? Well, if I try giving a double bond here, and let's give him his octet, so 2, 4, 6, 8 electrons, and over here we have a nitrogen atom with another double bond. How would that work? Well, this gives us, each atom has an octet now, 2, 4, 6, 8, 10, 12, 14, 16 electrons total were used. So this appears to be a valid Lewis diagram for the molecule, giving two double bonds and everybody has an octet. However, someone else might suggest that we could solve the problem by giving a triple bond to one of the oxygens. Let's try that instead. Suppose we gave a triple bond to an oxygen and a single bond to the other one, and we can apply resonance to that if we like as well, and then give everybody an octet like this. Notice we've used 2, 4, 6, 8, 10, 12, 14, 16 electrons again. So we have two possible diagrams. One where there's some symmetry with two double bonds, and one where there's asymmetry, a single bond and a triple bond to the nitrogen. How do we distinguish between the two? The answer is to calculate the formal charge on each atom. The formula for finding a formal charge is basically to take the number of valence electrons that the atom brought to the molecule, and then subtract the number of lone pair electrons on that atom in the diagram. Lone pair electrons belong entirely to that atom. And then subtract 1/2 of the number of bonding electrons. 1/2 because the bonding electrons are being shared between two atoms, so we're going to basically divide them between the two atoms. For example, if we take the top molecule here, the NO2 with the double bonds between both oxygens, we can see that the two oxygens in that molecule are equivalent. They both got a double bond and they both got two lone pairs of electrons. So I'm going to calculate the formal charge just for one of them. So the formal charge of oxygen in that molecule would be, using my formula, oxygen brings 6 valence electrons to the molecule, and then minus, there are 2, 4, so 4 lone pair electrons. Right? There's 2 here and 2 here, so 4 lone pair electrons. And then subtract 1/2 of the number of bonding electrons. And there were, a double bond represents 4 electrons in total, so 1/2 of 4. 6 take away 4 is 2, take away half of 4 is, take away 2 again is 0. So in the top molecule, the oxygens each have formal charge equal to 0. What about the nitrogen? The formal charge of nitrogen in that molecule, nitrogen brings 5 electrons to the molecule. Take away 0, it has no lone pair electrons in that molecule. And then minus 1/2 of 2, 4, 6, 8. It's got 8 bonding electrons. 5 minus half of 8 is plus 1. So notice when we go put these formal charges beside the atoms, the nitrogen here is plus 1, the oxygens are both 0. Notice that the total of the formal charges in the molecule equals the charge outside. So that has to be true. The sum of the formal charges must equal the charge out here that was on the ion. What about the formal charges in the second situation? If we calculate the formal charges there, we find, now notice the two oxygens are no longer equivalent. And if you're okay with this, I'll do this just verbally rather than showing my work down at the bottom. If we calculate the formal charge of the oxygen on the left, we would take 6, the number of valence electrons it brought to the molecule, take away 2, this lone pair here, so 6 take away 2 is 4, take away half of 6, 2, 4, 6. So 6 electrons, take away 2, take away half of 6. That leaves us with plus 1. That oxygen's formal charge is plus 1. If we do the same calculation for the other oxygen, it brought 6 valence electrons to the molecule. 6 take away 2, 4, 6, the lone pairs, is 0. And then minus half of 2, this bonding pair, would be minus 1. So we have plus 1 and minus 1. The nitrogen in the middle had 5 valence electrons, minus 0 lone pair electrons, minus half of 2, 4, 6, 8. So like before, its formal charge is plus 1. When we look at them, we notice that plus 1, and minus 1 still gives us the plus 1 charge that we had outside. So that part still works. The rule with formal charge is this, that the correct Lewis diagram will be the one that reflects the lowest possible formal charges that are closest to 0 on the different atoms. If you're looking at an ion, a molecule that has a charge, obviously there has to be a formal charge somewhere in the molecule. Negative formal charge should be placed on the atoms that are more electronegative. So if there's going to be a negative charge within the molecule, that negative charge should be usually on the atom that is more electronegative. If we look at those two basic principles, keep formal charges of the atoms as low as possible, and when there's negative formal charge, keep it on the most electronegative atoms, we notice that the first molecule here is the better choice. It has 0 and 0 for the two oxygens, and just one formal charge on the nitrogen. In the second case, the oxygens are no longer 0, they're plus 1 and minus 1. So we're breaking the first rule of formal charge, where we're able to keep the formal charges even lower with the top molecule. But the second problem is that we have this positive formal charge on an oxygen atom. Oxygen, of course, is the second most electronegative element on the periodic table, so it doesn't like to have a positive charge. So there's another strike against this Lewis diagram. So of the two, I'm going to rule out the bottom one. Although it looks like a possible diagram, formal charge on two different counts rules it out. It has higher formal charges in the top diagram, and it puts a positive formal charge on a very electronegative atom, oxygen. So for those two reasons, we're crossing it out, and we're going to say that this diagram is the correct diagram for the NO2 positive ion. So there's the last two concepts in Lewis diagrams that we need for AP chemistry: the concept of resonance, which is used to distinguish between equivalent Lewis diagrams, and then formal charge, which is used to distinguish between two diagrams that are not equivalent. If we look at one last example before we leave the video, let's take a look and apply what we've just learned. The bromate ion, BrO3 minus. See if you can draw its Lewis diagram. If we do some electron counting, there's one bromine atom, so that's going to be 7 electrons brought to the molecule. 3 oxygen atoms is going to be 18 electrons total, so that's 25 electrons. But the thing was -1, the charge, so we're going to add one more electron. We have a total of 26 valence electrons then to play with. Lewis diagrams do not promise to show the shape of a molecule, so don't worry about any kind of angles in the diagram. Just connect things properly. So the bromine is the central atom, and it's connected to 3 oxygen atoms. We've got 26 electrons to play with, and the whole thing has to have a -1 charge. Right now we've used 2, 4, 6 electrons, so we have 20 electrons left. The the 3 oxygens can each get an octet with 6 more electrons, and then the bromine could get an octet with 2 more electrons. So right away we see a possible Lewis diagram that jumps out at us. Okay, that looks like a perfectly acceptable Lewis diagram. Everybody's got their octet, and if we account for it, we can see that there's the right number of electrons. A total of 26 electrons have been used. But what about formal charges? If we look in here at the formal charges, the oxygens are all equivalent. They've all got a single bond and 6 lone pair electrons. So let's calculate the formal charge on the oxygens. The number of valence electrons for oxygen is 6, minus the number of lone pair electrons, which in this case is 6, 2, 4, 6, and minus 1/2 of the bonding pair electrons, in this case 2, this bond right here. So 6 take away 6 is 0, take away half of 2 is -1. So each of these oxygens has a formal charge of -1. That's a lot of formal charge within this molecule. The bromine in the middle, -1, -1, -1 adds up to -3. Since the whole thing is -1, this bromine had better be +2. Let's actually calculate that. Okay, its formal charge would be 7 valence electrons that it brought to the molecule. Take away the 2 electrons, which are the lone pair electrons. Take away 1/2 of 2, 4, 6, the bonding electrons, which indeed gives us +2. Now, it's a valid diagram at first blush, but those are really high formal charges. Is there a way to lower the formal charges? Well, we remember that bromine is an atom in period 4 on the periodic table, which means it's able to have an expanded octet. It doesn't have to be restricted to just 8 electrons. Oxygen, though, is in period 2. It cannot have an expanded octet. It can have a maximum of 8 electrons, and that's it, because oxygen has only s and p orbitals for bonding. But if we take these 2 electrons here and consider making a double bond to bromine, that would reduce oxygen's formal charge from -1 to 0. You can do the calculation to prove that to yourself. If we do that again over here, that'll reduce that oxygen's formal charge from -1 to 0 as well. That'll leave us with bromine having a formal charge, as we'll see in a moment, of 0 instead of +2, and the oxygen over here on the right, -1. Now you might say, well, why not do that for all 3? Well, let's try that. Let's draw 2 competing molecules. In 2 of them, I'm going to leave 2 double bonds and a single bond, and then over here, I'm going to draw 3 double bonds. Okay? In this case, we have 4 electrons each on those oxygens, the 6 there, and there was that lone pair here. If we add that up, let's just check that we had 26 electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 26 electrons. Formal charges are 0, 0, -1, and 0. If you want to just double check the bromine, it has 7 valence electrons, -2, and then -1/2 of 2, 4, 6, 8, 10, which is 0. Okay? This oxygen is still -1, and these are both zeros now. The one on the right, if we calculate its formal charges. We have 3 oxygens right now, all with double bonds, so if we give them their lone pairs to make their octets, and that bromine still had that lone pair here. If we add up everything here now, we see 0, 0, 0, which means this bromine should be -1. If we calculate its formal charge, we get 7 valence electrons that it brought to the molecule, -2, the lone pair electrons, minus half of 12, so -6, which gives us -1. So can you use the rule for formal charge to distinguish which of these Lewis diagrams is actually correct? We want there's 2 basic ideas. We want the formal charges to be as low as possible, and if there's negative charge, we'd like it to be on the more electronegative elements. So I think you can agree that the first diagram at the top is no longer being considered because its formal charges are just too high. -1, -1, -1, and +2. The bottom one on the left is actually looking pretty good. It's got 3 atoms with 0 formal charge and 1 with a charge of -1. But the one on the right appears to have 3 atoms with 0 formal charge and an atom with -1 also. So which one is correct? The key is that on the left, the negative formal charge is on oxygen, where on the right, the negative formal charge is on bromine, and the rule is that the negative charge should be on the more electronegative atom, which in this case is clearly oxygen. So we're going to rule out this guy, and we're going to suggest that this is the correct Lewis diagram for the bromate ion. Now notice, though, that there's 2 double bonds to oxygen and 1 single bond. If you think about that for a minute, you'll realize that there are actually going to be 3 contributing resonance structures that are equivalent to that. There's no reason to have these 2 bonds be the double bonds and this one be the single. We could easily imagine that the double bond is here and here, and the single bond here. Or we can imagine that the double bonds are here and here, and the single bond up at the top. If we consider those 3 equivalent Lewis structures, then we're talking now about resonance structures, and we realize that in fact the bromate ion should not have 2 double bonds and a single bond, but in fact will have 3 equivalent bonds that are resonance hybrid between single and double. So these are the 3 contributing resonance structures to bromate. Bromate is actually a resonance hybrid of those 3 contributing structures. So there is Lewis diagrams with the added description of resonance and formal charge.